Hi guys, welcome back to my channel. So today we're going to be looking at fuels and combustion, and specifically looking at the products of combustion and the energy output from the reaction of that combustion. So I've got three words in our vocabulary list for today. We've got fuel, energy, and of course combustion. Okay, so just quickly before we jump in and we talk about what's actually going on with the sort of chemistry, let's just go a little bit more general here to start off with. So I'm sure if you've worked in a job before, especially if you've worked, somewhere that has food cooking or whatever, one of the big issues in a lot of food service industries is dealing with fire. And really, there's three things that a fire needs in order to be burning, and that is, first of all, fuel. It needs some sort of heat source, like a match, and it needs oxygen. So a combustion reaction is really just burning something in the presence of oxygen. So if we remove one of these three pillars from this triangle, so if we either remove the oxygen, or we remove the heat, or we remove the fuel, then the fire will no longer be burning. So let's continue. That's just a sort of general little introduction there. So fuel is any compound that contains energy within its bonds and can burn in the presence of oxygen. So we burn food to make energy for ourselves, while most industrial processes will use various hydrocarbons or different petrols and fuels to power the work that they do. And combustion reactions are always exothermic, and we know that because we can actually feel the heat from the flame and we can see the light from the flame. So energy is being released in the form of heat and light. So generally, when a hydrocarbon burns in the presence of oxygen, if it's a clean burn, it will only produce carbon dioxide and water. So if I was to draw a quick little hydrocarbon here, every single one of these bonds between each of these carbons and with each of these hydrogens is going to be broken. Let me just finish drawing this. So each of these is going to be broken, and an oxygen is going to come along. Two oxygens are going to come along for each one of these carbons, and 3 carbon dioxide molecules would be produced. So that would be a clean burn where every single one of these carbons has been broken off to form carbon dioxide. So propane gas is commonly used in cooking and heating. So let's do an example using propane gas, writing the balanced combustion reaction of propane. So just as a little refresh, propane is an alkane, and we can calculate the number of hydrogens really easily for straight chain alkanes. So the formula that we use is going to be CnH2n plus 2. Propane, prop, that word means that there's going to be 3 carbons in the hydrocarbon chain. And so if I double this and add 2, that's going to become 8 hydrogens. So I've got C3H8, and that's going to be a gas because it's propane gas, and it's burning in the presence of oxygen gas, and it's going to produce carbon dioxide, which will be a gas, and water. And again, the water will just sort of depend on the temperature. It could produce steam, and generally if it's hot enough, it will just turn to steam anyway. So we'll just write that as a gas. Okay, so let's go ahead and balance this reaction now. So I always leave the oxygens till last, just because they're out on an island by themselves. It makes it a little bit easier. So let's go ahead and balance the carbons and the hydrogens first. So here we can see we've got 3 carbons and 1 carbon on this side, so we're going to triple the amount of carbon. We can also see we have 8 hydrogens on this side, and we've got 2 hydrogens on this side. So if we quadruple the number of hydrogens on this side, then we should also have 8. So let's go ahead and see how much oxygen we need now. So we've got 6 oxygens here, and we've got 4 oxygens here, so 10 in total. So we're going to need 5 lots of oxygen gas on this other side. So let's just quickly double check that's balanced. We've got 3 carbons, we've got 8 hydrogens, and we have 10 oxygens. Yep, good. So that's nice and balanced. Okay, so why use hydrocarbons? Why not use some other sort of fuel? Because if you've existed on this planet for like the last 5 years, you may have heard some discussion around climate change and the burning of fossil fuels. So why do we continue to use these substances to burn to create this energy? And it simply is because hydrocarbons, they actually have a lot of energy stored within their bonds, and we've actually done some calculations previously can't remember, but I have done it in a previous video where we calculated the amount of energy output from 1 mole of, I think it was propane gas. And it was in the, I think, the thousands of kilojoules for 1 mole. So it actually produces a huge amount of energy. And that's why we use it. So the energy output is always measured in joules. So that's the standard international unit that we always will use. But sometimes you may see some other units, and we've just sort of listed these below here. So nanojoule would be 10 to the negative 9, and that's because of that prefix nano. Same going up the other end. Kilo means 1,000, so we've got 10 to the power of 3. Tera means it's going to be 10 to the power of 12 joules. And those prefixes, those are always used, so you'll see them in front of other standard units as well. So products of combustion. And this is where a lot of this controversy lies with using fossil fuels, is the kinds of products that they produce as a result, because they don't always burn perfectly. So like I was saying before, we had that propane compound, and it has 3 hydrogens, and if it was to cleanly burn, that means that each of these carbons are being sort of snapped off, and each of them are reacting with oxygen to produce carbon dioxide. So that would be what I would consider a clean burn, because the only thing that you would see would be maybe a little bit of the heat or whatever, because this carbon dioxide gas is clear, so you wouldn't actually see the carbon dioxide gas. However, usually what ends up happening with these types of things, because there isn't enough energy available, or there's not enough heat, so remember that was one of the 3 parts of our heat triangle, because there's not enough heat available, it doesn't actually completely burn. So we might have something like propane, and I'm only going to actually have one of these compounds snap off. And if especially there's not enough oxygen as well as not enough heat available, we might actually see, rather than burning to form carbon dioxide, this is going to burn to form carbon monoxide. And then we're sort of left with this intermediate product over on the other side. And keep in mind, this has all its hydrogens attached. You might have like another oxygen or something attached to it if it's burning. But these kind of intermediate products, those are all those products that we see as that black sort of greasy sort of leftover residue. And especially if you've ever burned a fire or you know, gone camping and you've had marshmallows, you know that there's always some sort of ash or something left in the bottom. And that's because that tree or that bark, those really long chains of hydrocarbons in the bark, are actually really difficult to get a clean burn on. You need a high temperature in order to completely disintegrate that. So we often see a lot of those leftover intermediate products of combustion. So carbon dioxide, the main one that's produced. We can also produce carbon monoxide, so that's 1 less oxygen. And we can also produce these small solids, these small intermediate products that I was talking about, called particulates. And sometimes they're also called volatile organic compounds. And they're volatile because they're very gaseous. They spread very easily. But that's not the only thing, right? The other issue with burning these fossil fuels, with the carbon dioxide emissions and even with carbon monoxide emissions, it's not enough that, you know, we're producing these toxic compounds, but also the amount or the rate at which we are producing these compounds is continuing to go up. And so we're starting to see some of the longer term impacts of that. And we're starting to see these temperature changes, and we're starting to see these changes in our climate. So this is from, I've got the website down here actually. This is from this website down here. So if you wanted to go check that website out, they've gotten this data from the US Energy Information Administration. And most of the energy, so this is the total energy gained, is actually coming from the transportation industry. And this is in America, keep in mind. And primarily this is coming from petroleum. So, you know, long chains of hydrocarbon. So the other thing that we need to consider is that fuels do not only contain hydrocarbons, they also contain a whole bunch of contaminants, and these contaminants contain nitrogen and sulfur and oxygen and water. And so often we'll see a variety of things that are actually being produced. So I've got a full list here. So we've got sulfur, when that burns and when that gets into the atmosphere, that sulfur reacts with the clouds and it actually produces sulfuric acid, and that creates acid rain. So that's why this sulfur is a particular problem. When it rains, the acid rain, it actually leaches a lot of the nutrients from the soil. So it's not just the acid that's landing on the plants and the animals and stuff that's causing damage. It's actually also causing damage by leaching nutrients from the soil, especially metals. Nitrogen, these are often called NOxes, right? So you could have, they say nitrogen dioxide. Specifically, nitrogen dioxide is NO2, but we might also see NO3, or we might also see NO. So these compounds are all called the NOxes. So they're a group of very similar and related compounds. We also have nitric oxide. And again, these nitrogen compounds, they can react with water in the atmosphere to produce nitric acid. And it's a little bit less detrimental than the sulfuric acid. The sulfuric acid tends to be a little bit more common, but it is still a major contributor for acid rain. And one of the other things it can also produce is, of course, water, as we spoke about before, but that generally becomes steam, and we sort of lose that to the atmosphere. Okay, so how does this all relate? A lot of those compounds that I've just mentioned, especially, so what did we have? We had carbon dioxide. Now, carbon dioxide is probably the biggest one, just based on the sheer volume of carbon dioxide that's produced. Carbon monoxide, these are all greenhouse gases. So carbon monoxide, he's also a really big contributor, but there's less of carbon monoxide in the atmosphere. It's just that he's a lot better at holding on to that heat. So carbon monoxide is particularly problematic for us. A lot of those other compounds too, so those NOxes, for example, they're also capable of holding on to heat in the atmosphere. So it's not just the ones that are listed here. We've also got things like methane that are being released into the atmosphere. So those are as a result of those impartial sort of burning, so it doesn't fully oxidize. And also those sulfuric compounds, they can also sort of contribute to global warming and to climate change. So I'll just let you know, I've included this little link in your OneNote as well. This actually just discusses in a little bit more detail. I think that your textbook sort of very briefly touches on like a lot of different topics. I don't think it goes very deep into those topics. And I think this is such an interesting thing. And I think this was really pushed when I was in high school. And it was something that a lot of teachers really spoke about and that a lot of media was talking about. And it was something that was really prevalent in our textbooks. And everything always seemed to be under this lens of climate change. And I feel like that sort of fell by the wayside a little bit. And I think that was actually reflected in a lot of curriculum changes that had happened because it almost was like climate change was no longer spoken about in the curriculum. And so therefore, like it didn't exist anymore in a way. And I think that this is such an important thing. And I really don't think that we as schools and we as educators and as teachers actually place enough importance on speaking about this. So I've included an extra little link here for you. And that sort of just goes through and describes the impact of each of these compounds. So why do we care about climate change? And again, this is something, it's sort of spoken about, but it doesn't seem to be spoken about to the degree that it used to be when I was going through school. And it's just basically all of these compounds here, because they're so good at holding on to heat and holding on to energy. Usually what happens is the sun's rays, they'll come through the atmosphere and they'll sort of bounce back off here. But you've got all these like little sponges. And so instead what actually happens is it comes in and it's being scattered by those compounds. So it's actually going in all different directions. And then it runs into like another little compound. And so it scatters that in all different directions. And so a lot more energy is actually being scattered within the Earth's atmosphere and then can actually be held onto by these compounds. And in particular, water is really good at holding on to heat energy. And that's because it's got that high specific heat capacity. And so we sort of are creating like almost this feedback loop because we have all these compounds that are going into the atmosphere, like this big blanket. And then so that's causing more water to evaporate and that goes into the atmosphere. And then water is capable of holding onto that heat that's being stored or that's being scattered by all of these compounds, all these greenhouse gases. So it's just kind of this feedback loop where it's getting hotter and hotter and hotter. And if we don't actually stop this train, where are we going to get off? And I remember there was predictions that were being made in 2010. That's when I was a student, and predictions that were being made in 2010, and they were making all these claims for 2020, and now 2020 is here, and all of these things that they had predicted would happen if things did not change have since happened, and we are starting to see the result of that. There's been more variation in the climate. So in Australia, we're particularly impacted by El Nino and El Nina. And El Nino is when we have our periods of drought. El Nina is when we have our periods of floods. And it's really important to note it's natural to go through these cycles where we have droughts and when we have floods. But we have never had the severity of floods, and we've never had the severity of droughts and fires as we have in the last 10 years in Australia. And that's because these greenhouse gases, climate change, it's exacerbating these natural processes. And a lot of people think that, oh, well, it's okay because it's a natural process. No, we've accelerated that. If I was to put you on the treadmill and I was to say, okay, I want you to walk for the next 24 hours, you would be able to get on that treadmill and you say, no problem, I'll just get on there and walk. But then what happens when I start speeding up the treadmill? And you go, hold on a minute, you said that I had to walk for 24 hours. Now you're making me sprint for 24 hours. I don't think I can do this. And that's exactly what the planet is going through as well. So these natural cycles, it can go through. It cannot go through at this accelerated pace. And so it's really, really important that we take, global warming seriously. Sorry, a little bit of a tangent there, a little bit of a rant. So we've got some questions here, and I think a lot of these are pretty simple, and you should be able to go through these on your own. And I think what I might do, I might actually let you guys do this yourself, and I might actually make another video where I go through specifically this answer for question 3, because I have ranted a little bit today. Alrighty guys, I will see you in the next one.